Welcome to Group A2's video on tamoxifen. So how was tamoxifen discovered? Tamoxifen is a great example of when a drug has been discovered by accident but has achieved great effects. The discovery originated in two separate areas of research. In 1986, Dr. George Beatson removed ovaries from a 33-year-old woman with breast cancer and noticed a significant tumour regression in the following months. This sparked research surrounding the idea that the ovaries are a major estrogen source and estrogen is involved in the growth of tumours. Researchers around the 1960s were looking for new contraceptives. ICI 46474 was one of the contenders, which was then developed into tamoxifen. This will be explained later. Unfortunately, early forms of tamoxifen failed to have any contraceptive effect at all. Arthur Walpole then directed a study into cancer research and found that tamoxifen had a beneficial effect of treating breast cancer, as it acted as a full estrogen agonist in the mouse. In the 1970s, results of trials showed that tamoxifen was found to be effective in patients and had a relative lack of toxicity. The drug was licensed as a breast cancer treatment in 1972.
Tamoxifen did not suddenly pop up as a drug. It went through a long development process. After Dr. Beatson's discovery of the relationship between estrogen and breast cancer, doctors and scientists experimented with a variety of estrogen-like chemicals. One of these is silbestrol, which was developed by cancer research scientist Professor Charles Dodds in 1937 to try and treat breast cancer. Although at the time these efforts were successful, the side effects were too severe for widespread human use, so after 50 years of experimentation, the research hit a dead end in the 60s. The precedent molecule for tamoxifen, IC46474's development originally stalled due to lack of support and competing priorities in the UK company ICI. But then President Nixon declared a war on cancer, reigniting the interest in developing a drug for breast cancer. The R functional group shown in the structure of the original molecules are made to become an ethyl group, and this extra chain right here with a benzene ring, and tertiary amine, which give tamoxifen its agonistic effects. This will be further discussed in the next part of the video. Research later found that tamoxifen effects on cancer prevention, its mechanism of action, and how cells eventually develop resistance of this drug after 10 or 20 years. These findings may help tamoxifen to evolve and further develop into a better drug.
As with the majority of drugs, tamoxifen only has one isomer that is effective therapeutically. Only the trans isomer is active in the treatment. The cis isomer has no clinical use. This is the non-stereospecific route of the synthesis of tamoxifen. The first step of the reaction proceeds through Grignard coupling addition reaction, and a Grignard reagent, phenyl magnesium bromide, is added to the ketone 2-phenyl-butyrophenone to produce a tertiary alcohol. The next step is carried out under acidic conditions. A concentrated HCl can be used to remove the methyl group from the oxygen attached to the benzene ring. The Cl- from the HCl attacks the carbon. This pushes the electrons to the oxygen. The HCl protonates the OH group, making an OH2+ group, which is a good leaving group. The OH2+ group leaves as electrons are pushed onto it, making a positive charge on the carbon. The hydrogen from the OH group donates its electrons to the oxygen in the group and is later substituted in the next step. This molecule is then reacted with the 2-dimethylaminoethyl chloride in an SN2 reaction, where the molecule attacks the negatively charged oxygen. Also, the hydrogen donates a pair of electrons to form a pi bond between the positively charged carbon and the carbon it is attached to. This bond has a free rotation around it, therefore producing a cis and trans isomer. The trans or Z isomer is tamoxifen. Now on to the mechanism of action of tamoxifen. Tamoxifen is part of the SERM family, which stands for selective estrogen receptor modulator. This means its action is different in different tissues. So when tamoxifen binds to estrogen receptors in the brain or breast and mammary tissues, it behaves as an antagonist or anti-estrogen, preventing estrogen from binding to the estrogen receptor. But in the lungs, bones, and uterus, it behaves as an agonist. This information is found in the SPC for tamoxifen. But how does tamoxifen behave as an anti-estrogen? Tamoxifen has a similar structure to the synthetic estrogen diethylstilbene, with its stilbene core mimicking the action of estradiol. The main difference is the 4-amino ethoxy side chain, which is important for its anti-estrogenic effects. The side chain or tail can be seen clearly in the space-filling modules of tamoxifen and estradiol.